Low temperature is the inside of the house. The high temperature is the outside. There's 20 degrees of difference. And so in order to determine the maximum, the best, if this refrigerator was being operated at the perfectly reversible best case scenario, the coefficient performance would just be TC over TH minus TC. Okay? And that's because we can write the relationship between heat transfers and the temperatures. And so that's our expression for the refrigerator heat pump. In this case, the cold temperature is 530 Rankine, and the difference between the high and the cold is only 20 degrees. Okay? And so the maximum coefficient performance for this particular air conditioner is 26.5, which is fantastic. Okay? Again, the coefficient performance is related to the heat transfer that's being pulled out. In the picture here, it's labeled Q dot N over the work of the compressor. And so we know that that's going to be 26.5 or lower. And so if we use 26.5, and we know that Qn is 30,000 BTU per hour, all we have to do then is divide that Q dot N by 26.5, and that would give us the work of the compressor. That would be the minimum work required by the compressor. Okay?
What's the...
Okay?
Is TC 70 degrees before it's...
TC is 70 degrees before I added 460 to it.
How about label TL?
Low. Could be, okay.
Okay.
Low and high, or in or out, whatever. Yep, okay, thank you. And so that then would be the power. That would be the W sub C, the minimum compressor work to permit 30,000 units to be extracted. Now, they want to know the horsepower, and so I'm going to use the conversion factor that 1 horsepower is equal to 2545 BTU per hour. That is the conversion between horsepower and BTU per hour. And so this number then is 445. Okay, so if the system was operating as a perfectly reversible Carnot refrigerator, it would only need 4.445 horsepower in order to cause that amount of heat to be pumped. And so I think the question was, would it be sufficient to have a 3 horsepower?
Yes.
Well, I mean, let's take a look then. If it was 3 horsepower, what would be the beta? And so if it was 3 horsepower, the Q dot N over the work of the compressor for 30,000, and then if it was a 3 horsepower, I multiply that by 2545 to get these in the same unit, and this would mean that the COP was about 4.
Didn't I get this next?
What?
Should be. You increase the work by the compressor.
Uh-huh. Yeah. And so they're just saying that in reality, we have a system that's taking away 30,000, and 30,000 is how many tons of refrigeration? There's 12,000 in a ton, and so this is a 2.5 ton refrigerator. Air conditioner, yes.
So, if we do have a 3 horsepower, what is that 3.93? Is that telling us that we need more to get to the 26.5?
No, it just means, okay, this is reality.
Oh.
Reality is that the compressor draws 3 horsepower.
Okay.
And 30,000 is the heat in. I then calculated the real beta, which is a number very much smaller than the ideal. And so all they asked is, what is the coefficient performance, and is this probably sufficient? And again, we haven't had a lot of heat pumps and refrigerator, but that's a typical number
So that's
for.
sufficient.
Is it overkill?
No, it's probably not overkill. It's probably.
More than 0.445.
I mean, it's much more than that. I mean, we wouldn't expect to be able to, if the inventor said, I can do this task in a half a horsepower, you'd say, that's probably stretching it. If the inventor then said, I can do it with a 3 horsepower, you calculate the COP, and that's a typical number of what we see for refrigerators.
So if we did the actual data and...
That's the actual beta.
Yes, but if we found that was greater than 26.5, then it would be not sufficient, and we would have to take a horsepower that was greater.
So if the inventor said, I could do it with a 1/4 horse compressor, you would put a 1/4 horse in here, and the number would be greater than 26 and a half, and you'd say no.
That's not.
Because the best that you can do would be minimum is 0.445, transferring heat between those two
That's
temperatures.
only if it was reversible.
That's only if it's reversible.
This doesn't account for the loss.
Yeah.
This accounts for the losses. This accounts for entropy being generated.
Because all it seems like it's doing is changing the compressor on it. If
Yeah, we are.
looking at this, all I would do is just go buy a half-horse compressor, plug it in, and it would work perfectly fine. But is that not true?
No, a half-horse compressor would not work perfectly fine.
And why is that what we
Because the real system would probably only have a COP of 4, and if you had a half-horse compressor, you might only be able to transfer about 6,000.
Yeah, but how can we judge what the rest of the system is doing if all we're changing is just the work of the compressor? That makes sense? Because it says in the problem that we chose a 3-horse compressor.
Okay.
So if that's the only thing that we're changing, then why can't we buy a half-horse compressor and have it work perfectly fine? Where else is all the losses?
Okay, there's always going to be losses, and we'll go through the losses, but in the case of a half-horse compressor, you probably would only be able to pump 1/6 of the refrigerant around the cycle, doing what you want it to do, and that 1/6 would only probably transfer, out of the house 6,000 DT per hour. So it'd be undersized.
But if we choose a half horsepower
Yes.
engine or
Compressor?
Then the beta would be 23.6, which is less than the 26.5.
Well,
so
it would-
how do we know in our head that that's not sufficient?
Yes.
Are we supposed to just make an educated guess?
Well, we would look at the non-Carno, and we would actually look at where the losses are, and we figure it out.
So technically, we can't figure that out from these equations. We didn't.
All
figure
you
any
can
of that out.
do, all we have been able to do in this chapter is look at the ideal scenario. The ideal scenario is the Carnot cycle with absolutely no irreversibility, perfect type of cycle. And all we can do is determine the peak between the two temperatures. We can determine the minimum amount of work required to do this task.
So when it asks if the compressor is sufficient for this system, the answer is yes. It's sufficient. It will run the system, but not at its peak performance.
So the question is, might the net power input be of 3 horsepower be sufficient? Once you calculated this value to be 4, your experience and previous other calculations of real systems would have indicated to you that that's a quasi-possible COP. And then the answer is if yes, determine the coefficient performance, and that's what we just did. So you kind of had to. What they were first asking in that question is, do this, and then if I had a 3, should I possibly, it's not out of the realm of not working.
Yeah.
And so we say yes to the first question because it is higher than the minimum. And then if we said yes, which we did, we then calculated the COP so that we can then answer another question.
Should we know based on our experience that is more appropriate in some way?
Yes.
Well, I didn't fully understand what we did previously, so.
Well, we haven't really done refrigeration. That's chapter 8. Okay, so we'll get there. Let's look at 560, and let's put a few other numbers on to a heat pump. And in this one, we have a heat pump cycle. The job of this cycle is keep the interior of a building at 20 degrees Celsius. At 20 degrees Celsius, it's a heat pump, and so this is going to be this 20 degrees Celsius, 293 Kelvin is going to be the TH. Okay, that's the inside of the house, and reading through the problem, that's going to be the high temperature that we're expecting this heat pump to pump energy into. At steady state, the heat pump receives energy from a well water at 10 degrees Celsius. So down on the other side, the well water is at 10 C. And so that's 283. And that's Kelvin, and that's going to be our low temperature reservoir. So we're running this heat pump between these two temperatures. And so what we're going to do is we want to pump in the problem, this cycle, this refrigeration cycle is wanting to pump in 120,000 kilojoules per hour. This is Q sub H. Into the room. This is the room. Over a period of 14 days, the electric meter records that a certain number of kilowatt hours of electricity is provided to the heat pump. And so we've got this, we've got this work of the compressor, and we're paying for the energy that particular compressor is requiring. And so they want to determine the amount of energy that the heat pump receives over 14 days from the well water by heat transfer. So we're interested in the Q sub L. Okay? So for 14 days, the power bill was $14.90 kilowatt hours of electricity. Okay? And we're going to make the assumption that this system is running continuously. Okay? So making the assumption that it's running continuously, what can we say about the work of the cycle? The work rate of the cycle. We know that we're using 1490 kilowatt hours of energy, and how many hours did we run? 14 days times 24. And so by dividing the number of hours into our usage in kilowatt hours, this allows us to determine the kilowatt energy going into, going in as the compressor power. Okay. Okay. So, in order to get it into the same units as my solution, I'm going to take this one step further and this is kilowatts, is it not? And I'm going to then turn that number, I'm going to divide by, since a kilowatt is a kilojoule per second, right? I'm going to multiply this by, let's see, I'm going to, I see what they did. Okay.
There's still seconds.
Now, okay. They didn't go this route. Let's see. Instead of this number here, okay, 1490 kilowatt hours is a unit of energy. And what I'm going to do is I'm going to divide that by what an hour is. An hour is, I'm going to multiply it by 3,600 seconds in 1 hour. And so now what do I have? Since the hours cancel and a kilowatt is a kilojoule per second, the seconds will cancel. And so this will tell me then the total amount of kilojoules that went into the compressor over that 14 days. And that was 5.364 times 10 to the 6th kilojoules. Okay, so that's the work that went in during the 14 days. My meter said this number of kilowatt hours, and I know that an hour is 3,600 seconds. A kilowatt is a kilojoule per second, and so my seconds cancel, and I end up with kilojoules.
So it's actually kilojoule per second hours.
No.
Well,
Yes, what the meter gives you is kilowatts or kilojoule seconds times an hour. Okay.
it's all we cancel out is kind of 6 seconds per hour. Kilojoules per second.
Okay. One conversion that we could have used is this one right here. That 1 kilowatt of energy is 3.6 times 10 to the 6 joules. Okay, a kilowatt hour is 3.6 megajoules. How did I get that? I got that because 1 kilowatt, that's 1,000 joules per second. And then what is an hour? An hour is 3,600 seconds per hour. And so when I cancel the seconds, and then I have that extra hour here. You know, this kilowatt is this, and then I have an hour. The hours cancel, and so I get 36 megajoules, 3.6 megajoules. So that's a conversion for what a kilowatt hour is. And so I could have just taken, yes, I could have just taken this number times this number. I have another factor of 3 in there because this has been written in kilojoules. And so 3.6 times 10 to the 3rd kilojoules is what a kilowatt hour is. Okay. And I could have just taken this number times this number and got that number. So during the 14 days, over here, I've put in 5.364 times 10 to the 6 kilojoules of energy in the form of work. Okay, now let me do the same thing on the high side. What do I have here? I have 120,000 kilojoules per hour, and then I multiply this by 24 hours times 14 days, because it's 24 hours in a day. And so that's going to also give me, that's going to tell me what my Q sub H is. And so my Q sub H is 40.32 times 10 to the 6 kilojoules. The reason they wrote it that way is they want to keep the 10 to the 6 kilojoules as a common multiplier. Okay, so you see what I did up here? Every hour, 120,000 kilojoules are being transferred into the house as heat. We're doing it for 14 days at 24 hours a day. So 40,000 times 10 to the 6 kilojoules is what's pumped into the house. What did it take, how much did it take to do that? This number right here. So we should be able to then determine what QL actually came from the water. I know that this number plus this number has to equal that number. And so we could then say that QL is 34.95 times 10 to the 6 kilojoules.
I'm sorry, what did you subtract from what, or what did you add to what?
I know that QL plus the work of the compressor has to add up to the QH. We've written that a number of times in a number of different ways. We've said this, and we said on a rate basis, and so all I really did was I solved for QL as being equal to the QH minus the work.
And you have to.
Yes.
It's the vibe. I'm still way over here. I'm trying to figure out what the vibe is. So if you
Which one are you trying to figure out?
The 5.3. If you multiply and you use the conversion that you said, it gives you 5.3 times 10 to the 9.
But then this is kilojoules. So I backed off by 3 to get it into kilojoules.
Okay.
Sorry about that.
No, it's fine.
Okay, so having done the numbers as they specified in the problem, okay, so part A was the amount of energy that the heat pump receives over the 14-day period from the